Okay, gang. Welcome back to Calc 1. Today we are going to talk more about differentiation and the derivative. Specifically today we're going to start talking about the derivative as a function in its own right. We're also going to go over some theorems and definitions. Now I do want to say a few things before we get started. Next week we're going to have our first 2 rounds of student teaching. Haley and Tahara are going to be doing section 3.1 at the start of next week. And then Thomas is going to be doing section 3.2 in the middle of next week. So if you're doing some student teaching, remember I need rehearsals, we need actual content run through before your day. If you're doing a collection of short YouTube videos or something like that, you can just send them to me, just upload them to your own channel or wherever you want, and then send me links so I can review them. And if you're doing an actual live lecture, which I think is Thomas's intent, then we'll need to do an actual rehearsal before the day of the lecture itself. And I just want to remind you guys that we need to do those things. And for those of you whose student teaching is not next week, but is coming up soon, we do have plenty of folks doing chapter 3 and 4 and 5 things. Don't wait, don't procrastinate getting ready. You want to be putting some effort in now. The other thing is that you also want to be working on your honors projects. So let me go ahead and we'll make these a part of official announcements. Student teaching begins next week. You must meet with me in office hours a week beforehand to discuss materials and prep. Then we need a rehearsal. Before the day itself. I'll get rid of that thing. All right, so this is important. We want the student teaching to go well. I want everybody to get 100% on this. And I want your peers to get everything they possibly can out of these lectures. So it's not just a responsibility to you for your grade purposes, it's also a responsibility to your classmates to make sure that they have a good and strongly positive experience with your lectures. So we need to meet a week beforehand, no later than that, to discuss materials and exactly what you're going to do. And then we need a rehearsal sometime before the day itself. If you're doing YouTube videos, you can just upload them and send them to me, as long as it's like 3 or 4 days before your actual teaching day. So I have time to look at them and let you know if anything needs to be changed or re-recorded. If you're doing a live lecture, then we need to meet at least a couple days before your actual student teaching day so that we can run through your live lecture and make sure everything is as it should be. That is all. And then the other thing here, kind of announcement, please begin working on your honors projects. I think, see, now that I'm remembering, I think some folks asked me for some examples of past honors projects. I don't know if you guys will be able to get into into this thing, but there should be timelines, handouts. Interviewing, advising classes. Somewhere in here, I should have some samples. Sample past honors media presentations. Yeah. So let me see if I can, if you guys are going to be able to follow this or not. Oh, here we go. So I'm just going to paste these URLs into the chat for you. That way we don't have to worry about Canvas permissions. Here are some sample honors presentations for comparison. All right, and I would just copy paste that out of chat into a Word document or a Notepad document or something like that. So you can see what some past honors project presentations looked like. And I think there's a couple more here. And then Jason, one of our old teachers, since moved on to bigger and better things, he has a little guide here. So maybe I will save this and share it with you somewhere you can get at it. Topic, modifying textbook questions, interest. Yeah, this is pretty good. I will go ahead and save this. No, not that. Spring 2021, your class, JH. And I'll upload that to our course modules here. So Professor Harrington, Jason Harrington, is a nice guy. He ran the math lab for a while. He was also involved in the math team. He did a lot of things before he left that I do now. I trust his judgment, his writing, all of that. So I'm going to add a module here for, do I have an honors thing yet? No. All right, so I'll add a module here for honors project. See, can I upload a file here? Files, I'll have to come up here and upload it. All right. So do take a look at at those links I sent you in the chat. Save those somewhere. Save that whole chunk of stuff there somewhere. And then you can come to our modules and look at Professor Harrington's research guide. That will be useful. So project stuff, assignment file, JH research guide. Here it is. All right. And published. Cool. So those are some things that you guys can be looking at for inspiration to help you shape your project. Remember, you're required to do three things. You need to write a research paper. You need to put together a presentation, like a PowerPoint or TIX presentation, something like that, Beamer, or and you need to put together a little poster. I recommend writing the paper first, right? Write the paper and then build your presentation around that paper, right? Your presentation will be essentially you discussing the things that you discuss in your paper. So I'd do them in this order: research paper, presentation, and then the poster. The research paper is where you're going to actually do all the work. Then the presentation is really just you kind of summarizing the work you did in the research paper, maybe with some samples or examples or things like that, demonstrations. And then the poster will be kind of a static version of your presentation that people can come up to and read if they aren't able to watch your presentation. So just those little notes on honors stuff. Today in class, we're going to talk about section 2.8, which is on the derivative as a function. So recall, given a function f primed of x, we can find the slope of the tangent, which we called m tan, right? Slope of the tangent. Slope of the tangent at x equals a as m tan, which we call f primed of a, and that was the limit as h goes to 0, f of a plus h minus f of a all over h. And today we're going to start thinking about this. Previously, we thought of this as a constant, right? It's the slope of the tangent line at one particular point. But now what I want to start doing is thinking about all of the slopes, right? So I want to start thinking of this base point A, instead of being a constant, as being a variable. The slope of tangent at the constant input A. Now we want to think about f primed of x. So I'm going to let the inside here go from being a constant to being a variable. I'm going to start thinking about, instead of one slope of a tangent line, all the slopes of the tangent lines. And this is defined how you would think it is. Lim h to 0, f of x plus h minus f of x all over h as a function. Of x. All right. So just a relabeling, right? I'm swapping the a's for x's, but the conceptual shit is where it gets good. In order to kind of build up to this, I'm going to look at a few specific examples, and that's going to lead us in the direction of a few really interesting theorems. I need to close this paren, don't I? Yeah, slope of tangent to the constant input A. So let's do it. I'm going to give us a specific function, f of x. We are going to, rather than calculate, we're going to approximate the slopes of the tangent lines, and we're going to use that to sketch a graph of this thing called f primed. So our first example for the day, let's have f of x be x squared. I'm going to graph this, and I'm going to pay a little bit more attention to the scales than I normally do. It's not going to be as rough a graph as my graphs normally are. I'll try to be a little bit careful. I'll mark this as 1, 2, 3, -1, -2, -3. Mark this up here as like 9, and a little less than halfway down, that would be 4, and then a quarter of the way there would be 1. We know what the graph of this thing looks like. It goes through -3, 9, -2, 4, 1, 1, -1, and 1, 1, 2, 4, and 3, 9. Of course, it also goes through 0, 0. So my curve here, this is a parabola. We know what these look like. They look like this. Something like this. What I want to do is at each of those points, get in there and approximate the slope of the tangent line. So for example, over here, if I draw just a little sliver of that tangent line, I want to kind of take a guess. Over here, I'm going to draw just a little sliver of this tangent line and take a guess. Over here, I'm going to draw just a little sliver of this tangent line and take a guess. So let's look over here, way over here. This slope is definitely steep and negative, right? Like a -1 slope would be like this, -2 slope would be like this, -3 slope. This looks to me like it's -5, -6, somewhere in that range. Over here at this point, the tangent line is still sloped negatively, but it's not as steep as this, maybe like -4. Over here, the tangent line is still negatively sloped, but not as steep. And I would say it's like -1, -2, something like that. And then by symmetry, over here, since this is symmetric about y = 0, the slope of the tangent line here, I would estimate this to be 2. Here I would estimate this to be, well, it's got to be the positive version of this, 4. And over here, this really steep one, it's got to be the positive version of this, so that would be 6. Is everybody comfy with what I'm doing here? These are just guesses. I'm not doing any calculation. I want to be clear about that. Are there any questions about this? Okay then. So based on what we have here, what is f primed of -3? We think that this is approximately what? What was our guess?
-6.
I'm sorry, Hulu, could you just say that a little louder? I didn't, my volume must have been down.
At the point of tangency on f prime -3 will be -6 the slope.
Yeah, beautiful, right? So the point of tangency here, this is at x = -3. So f primed of -3 is the slope of the tangent line at -3, which we said was -6, there or thereabouts. F primed of -2. According to our guesses here, what do we think f primed of -2 is?
-4.
Good, yeah, -4. All right, f primed of a is the slope of the tangent line to f of x at x = a. So all of these values we just guessed, those are values of the derivative. F primed of -1 would be the slope of the tangent line at -1, that's -2. I didn't draw it in here. What is f primed of 0? What's the slope of the tangent line right here at the vertex?
0.
Good. That one we're actually confident about. That's not a guess. We can be certain of that. And then by symmetry, f primed of 1 is 2. F primed of 2 was 4. And f primed of 3 was 6. What I'm going to do is use these guesses to sketch the graph of the function f primed. F primed is the function that takes in x values and spits out slopes of tangent lines. That's the function whose input and output pairs I've described over here. So if this is f of x, then down here I can graph f primed of x. And I'll do that. -1, -2, -3, 1, 2, 3. All right. I guess I need to mark off some y values too. I'll call this up here +6, and I'll call this down here. What is the distance down here? This -6. So f primed of -3 we think is about -6, which means -3, -6 should be on the graph of f primed. F primed of -2 we think is -4. So if this is 6, then this would be 3, so 4 would be right here. So f primed of -2 should be -4. So -2, -4 is on the graph of f primed. F primed of -1 should be -2. F primed of 0 is 0. F primed of 1 should be 2. This is 1 and 2. F primed of 2 should be 4. So this would be like 3, 4, 5, 6. 2, 4. And then f primed of 3 we said should be 6. Well, what we have down here is the startings of the graph of the derivative. And if I connect these points, this looks to me, my art is bad and I feel bad. This looks to me like a straight line. No. I need some fat points to actually make this a straight line, but doing my best here. Modulo my bad art, here's the graph of our derivative. All right. Now, what is this function? What is this line I've graphed here? Well, the y-intercept is 0, and the slope is 2. So it looks like f primed of x, my guess, is that the function f primed of x is 2x. And there are some beautiful connections between the graph of f prime and the graph of f. Notice that everywhere f is decreasing, f primed is negative. Everywhere f primed is everywhere f is increasing, f primed is positive. If you look at these two graphs together, you can start to make connections. And this is what the second part of your homework this week is going to be. You guys are going to be given graphs like these, graphs of the original function, and you'll be told to sketch the graph of the derivative. Now it's WebAssign, so I can't like make you sketch the graph. It's going to tell you to pick between 4 graphs, but you need to draw them. You need to go through this exact process and draw your own graph. And then say, okay, which one of the graphs there looks like the graph I drew? If you don't go through that process, you won't learn the shit, I promise you. If you just like click around until you get the right one, it's not going to do the same thing. So please, on the problems that give you the graph of the original and say sketch the graph of the derivative, really sketch the graph of the derivative. Copy down the graph of the original, get in there and draw in some tangent lines, guess at their slopes. It doesn't have to be perfect, just guess at their slopes, and then use that to sketch a graph of the derivative, exactly as we've done here. Are there any questions about that process that I want you guys to go through for the homework?
If while trying to guess a slope, if it's not accurate, do we just calculate the derivative at the point of tangents?
No. So your goal there is just to come up with a picture. And if these aren't perfect, if these estimates aren't perfect, you will still come up with a good picture. So if I got this wrong, if this was like -5 instead of -6, or if this was -3 instead of -4, I would still, after plotting those points, I would go, oh, this kind of looks like a straight line, right? So even if you're off by a little bit, it's okay. It's all right. Your graph will still have the right shape. It might not be 100% perfect, and you're going to need to use a little bit of logic and reasoning to get to a place where you're getting good graphs. But I'll just show you an example of a problem that I'm talking about. This here is. This is not going to work because it never does. Thank you, Cengage. Right, so here's you guys. So you get down here, right? There are no actual numbers. So I want you guys to copy down this graph and then go in there and just guess at some slopes of tangent lines. It doesn't have to be anything perfect. There is no quantitative analysis here. They're not even giving us any numbers. So it's just about like guessing and trying to get the shape. So you would come in here, you would sketch this just like we sketched x squared up there, just like we sketched x squared here. Guess at the slopes of some tangent lines. So sketch this, guess at the slopes of some tangent lines, and then sketch your graph like this. Once you have your graph like this, you'll go back over here and go, okay, which one of these 4 graphs here kind of looks closest to the graph that I sketched? Does that make sense?
Yeah, thank you.
Cool, cool, cool. All right. We can check this. This is our guess. And we can check it because we know how to calculate the derivative. It's just that limit. So let's check our guess. If f of x is x squared, then by definition, f primed of x is that limit. F primed of x is equal to the limit as h goes to 0, f of x plus h minus f of x all over h. And this is a limit I can calculate. I need to put in for my function f what it is. So this is lim h to 0. If f of x is x squared, then f of x plus h is x plus h squared. F of x is just x squared, and h is just h. So I'm going to try to calculate this limit raw. Nobody can stop me, except perhaps my dying pen. I may have to switch colors on you guys here. I'm sorry. I will try to avoid it. But let's see what we have here. So it'd be lim h to 0. I have x plus h all squared. That's x squared plus 2xh plus h squared. And then I'm subtracting off x squared. And all of this is still being divided by h. And the x squareds, they go and talk to each other a little bit. This guy is going to be like, hey, how you doing? And they're going to be like, let's get out of here. So they're going to leave. And what's left is lim h to 0, 2xh plus h squared all over h. I can factor in h from the top. So I'll have lim h to 0, h times 2x plus h all over h. And now these h's are like, let's get out of here. And we're like, okay. So what's left is limit h to 0, 2x plus h. The denominator, when you cancel the h's, becomes 1. And the h from the top goes. So this is now that the h from the bottom is gone, we can just plug in h equals 0 to calculate this limit. This is 2x plus 0, or just 2x. So we were correct. F primed is equal to 2x. Our guess was correct. And this is that new function called the derivative. Someone in my last class asked a really cool question that I want to share with you guys. She said, okay, if we start with this function and we run it through this process and we get 2x out, does that mean if we started with 2x in this process, we would get x squared out? What do you guys think? It's a cool question. Operations like that, there are some operators out there like that, where if you do the operator twice, you end back where you started. But here, we certainly could run this new function through this operation again, but we would not get out x squared. If you wanted to take the derivative of this, you would look at the slopes of the tangent lines here. And the slope of the tangent line everywhere along here is the same. It's always 2. So if you wanted to differentiate this again, right, like here's the original, here's the derivative. If you were to differentiate the derivative, instead of going back to the original, you would get out the constant function 2. Because the slope of the tangent line here is 2. The slope of the tangent line here is 2. The slope of the tangent line here is 2. The slope of the tangent line everywhere here is 2. So it's not true that this is an idempotent operator. That's the name for an operator that when you do it twice takes you back to the original. But there is a way to go back. There is a way to undo this process. Remember, this is called the derivative. Undoing this is called the antiderivative. And we're going to talk a lot about that at the end of the semester. That's one of the main focuses in Calc 2. But we're not there yet. So what we've just shown by calculation using the definition is that our guess was correct. Right? We have verified this guess. If f of x is x squared, then indeed f primed of x is 2x. And if you think about just the algebraic shape of x squared compared to 2x, you might notice some things that look like patterns. And next week, Haley and Tahara are going to show you that those patterns are indeed correct in general. But that's not the goal today. The goal today is to get more practice at this sort of thing, going from the graph of the original to the graph of the derivative, and through this approximate process. Now we can verify, because here we do have formulas for the function f of x, which means I can come up with a formula for f primed, but it's mostly the picture thing that I'm worried about today. This is what I want you guys practicing. So we're going to do another one of these. Questions on this before we move on? Questions on the picture, how we went from here to here, or how we got these approximations for the value of the derivative. Questions on the calculation that we used to verify our guess? Any questions on what we did here? Okay then, let's get some more practice with this shit. This time I'm going to begin with a slightly stranger function, not altogether different. I'll phrase it as it will be in your homework. Use the graph of f of x below to sketch the graph of f primed of x. Now the function I'm going to use here is one that you guys know, and we'll get into talking about the algebra and stuff in a minute, but I want to begin just by focusing on the picture. Okay. So this is the point 1, comma 1. This is the point -1, comma 1. Over here is the point -2, comma 2. Over here is the point 2, comma 2. So the function here is the absolute value function. We can add one more over here at -3. We want -3, comma 3, 3, comma 3. Again, my art isn't perfect, but absolute value function. If we come in here, my speed point, what is the slope of the tangent line at this point? It looks like -1 to me, right? So we want the slope, right? What is the slope there? It's true that the x value is -3, but the slope here is -1. And the same is true here. If you draw in this little bit of the tangent line, the slope of that tangent line is the same as it was above. And here the slope is the same, right? This is a straight line. They all have the same slope. And if you play that same game over here, if you draw in a little tangent line, this looks like it has slope +1. And this guy looks like he also has slope +1. Everywhere here, the tangent line, it's the same line, right? The slope is just +1 over here and -1 over here. So based on these estimates, what would you say oh shit, let me do it over here. What would you say f primed of -3 is?
-1.
Yeah, good. -1, right? It's the slope of the tangent line to f of x at x equals -3, which is -1. And this is the same as the slope of the tangent line at -2. So f primed of -2 would also be that. So is f primed of -1. In fact, f primed of x appears to be -1 for all negative values of x. Everywhere to the left of 0, the slope along this graph is -1. And similarly, if we come in on the other side, f primed of 1 is 1, and that's the same as f primed of 2 and f primed of 3. And in general, it looks like f primed of x is equal to positive 1 for all positive values of x. Well, what does that look like? If I want to sketch a function that is equal to -1 everywhere x is negative and equal to positive 1 everywhere x is positive,
Two straight lines, I would assume.
yeah, exactly. F primed, so here's the graph of f primed of x that we're going to try to sketch. F primed of -3 is -1, so -3 comma -1 is on the graph. F primed of -2 is also -1. F primed of -1 is also -1. F primed of -1/2 and -1.5 and -2.5, all of those would be down there. So it looks like this horizontal line over here. I don't know what happens at 0. I'm gonna just say, okay, well, I know if I'm really close to 0 over here, like even -0.01, that's still like right here, where my slope would be -1 all the way up to 0 itself. But at 0, I cannot say. It certainly isn't -1. Everywhere to the left of 0, that slope is -1, but at 0 itself, I don't know. We'll deal with that in a minute. Over here, on the positive side, if x is equal to 1, I know that f primed of 1 is 1, because the slope here is clearly 1. F primed of 2 is 1. F primed of 3 is 1. F primed of pi would be 1. F primed of the square root of 2 would be 1. F primed of 0.01 would be 1. Everywhere over here, the slope is positive 1. So if I'm graphing just the slopes, then everywhere to the right of 0, just like over here, everywhere to the left of 0 is -1, everywhere to the right of 0 would be positive 1. And as we sneak up and get closer and closer and closer to 0, those slopes all stay positive 1. So we can bring it in really close. But at 0, again, hard to say. So the big question here, what is f primed of 0?
That doesn't exist.
That's going to turn out to be the case. Yeah, f primed of 0 does not exist, and I'll prove it to you in a minute. But first, can we write down a formula for this derivative? Can we use the piecewise function notation to write a formula for the function f primed of x that's graphed right here? What does this look like to you guys?
Y equals -1 for all x values less than 0.
Good, yeah. This thing only ever outputs two numbers. It either outputs -1 or +1. It outputs -1 if x is less than 0, and it outputs +1 if x is greater than 0. And then the question is, could we fill in the 0? Is there something we could put in here? Could I fill in this hole, or maybe I fill it in here at 0, or put a filled in dot anywhere along the y-axis that would be true? And what we need to answer that is the limit definition of the derivative. Now it's evident from the graph here, right, that the slopes here really are always -1, and the slopes here really always are +1. So I'm not terribly interested in going in and like proving that this is the correct formula for that guy, because we know it is. It's not, these aren't guesses, right? I can actually tell what the slope is here. I can actually tell what the slope is here, so I'm not guessing there. But at 0, I want to look really closely. I want to use the limit definition to try and settle the question, what about f primed of 0? So Let me grab some fresh paper. I'll hold on to this one, but I'm going to let go of this. So we want to know, do it like this. Is there, can we determine f primed of 0 for the function f of x equals the absolute value of x? We can try. We would use the definition. By definition, f primed of 0 would have to be the limit as h goes to 0, f of 0 plus h minus f of 0, all divided by h, which is lim h to 0, absolute value of 0 plus h minus the absolute value of 0 all over h. 0 plus h is the same as h. So this first piece is just the absolute value of h. Minus is minus. The absolute value of 0 is 0. And all of this is over h. So we get lim h to 0, absolute value of h over h. And I don't know what the graph of this looks like. Maybe you do. Let's pretend like we don't. The way we need to attack this is by looking at left and right limits separately. To get rid of the absolute value, we must consider the limit as h goes to 0 from the left, abs h over h, and the limit as h goes to 0 from the right, abs h over h, separately. If h is going to 0 from the left, that means h is negative, right? If you're sneaking up on 0, but you're coming in from the left-hand side, that means you're smaller than 0. That means you're negative. And the definition of the absolute value function the absolute value of anything is equal to that thing if that thing is greater than or equal to 0, and the negative of that thing if that thing is less than 0. This is how absolute value works in terms of algebra. If you're positive, it leaves you alone. If you're negative, it slaps another negative on to make you positive. So when looking at the limit as h goes to 0 from the left here, we're considering h's that are negative. So the absolute value of h upstairs is the negative of h. So this is lim h to 0, negative h over h. And now you can cancel the h's. That's lim h to 0 of negative 1. And the constant function negative 1 has limit negative 1. On the other hand, if you're sending h to 0 from the right, then the absolute value of h is just h itself. And the h's cancel, and you get lim h to 0 of the constant function 1, which is 1. So lim h to 0 abs h over h, the overall big boy limit, does not exist. And that limit was, by definition, f primed of 0. So since f primed of 0 was equal to the limit as h goes to 0, abs h over h equals dne, we say that f primed of 0 does not exist. Which is exactly what you said a minute ago, right? That the derivative at 0 does not exist. There's a special term for this. It's called differentiability. In other words, this really is the correct derivative. There is no way to fill in this hole here. If you filled it in down here, that would be wrong. If you filled it in up here, that would be wrong. If you filled it in at 0 or anywhere else, that would be wrong, because f primed of 0 does not exist. The way a mathematician would say this is that f is not differentiable at x equals 0. And that's the term I'm going to define for you now. It's getting hot up here. Okay. So ready for some definitions. If the limit defining f primed of a exists, then we say f of x is differentiable meaning like can be differentiated at x equals a. If the limit defining f primed of a does not exist, then we say the original function f of x is not differentiable at x equals a. So very much like continuity, differentiability happens one point at a time. I can talk about whether a function is or is not differentiable at one number. And if you want to check whether or not a function is differentiable at a number, you need to check whether the limit defining the derivative at that number exists. We can extend this in the same way we extended the definition of continuity. We say f of x is differentiable on the interval capital I, where I is, whatever interval you want, interval a, b, closed, open, whatever, on the interval capital I, provided f of x is differentiable at every number A in the interval I. So here what we're defining is differentiability on an interval. And then we'll say f is differentiable full stop if it's differentiable everywhere, right? If it's differentiable everywhere on its domain. So it's very similar to continuity, right? These definitions should look very similar to the associated definitions for continuity, where we said a function f of x is continuous at x equals a if some limit statement is true. And then we say f of x is continuous on the interval I if that limit statement is true for every number a within the interval I. The similarity between these two things is hinting at a theorem. A theorem connecting differentiability with continuity. So what might be true about continuity as it relates to differentiability? What does our brain want to say? Remember, continuity means like connected, one piece. Or maybe better, what isn't true about continuity and differentiability? Let's look back here. Is this function, the original function here, continuous everywhere?
Yeah.
It is, right? This is continuous everywhere. This graph right here, the graph of the absolute value function, it's one piece, right? I can lift it without drawing my pen. Bam, bam. It's continuous at all real numbers. Is it differentiable everywhere? Yeah, no, it's not. Where is it not differentiable? Good. So this function is continuous everywhere. It's differentiable at -1 and -2. It's differentiable at +1 and +pi, but it's not differentiable at 0. It's continuous at 0, but it's not differentiable there. So if there's a theorem relating continuity and differentiability, what could that theorem not say? What tempting thing isn't true?
Like a function could be continuous at all, like in the entire domain, but it doesn't mean it would be like necessarily differentiable.
Good, yeah, perfect. So here's something that took mathematicians a surprisingly long time to figure out. There was a period of time where we thought all continuous functions were differentiable. But it's not true, right? The absolute value function right there is a counterexample to that claim. So what isn't true is that if you're continuous, then you're differentiable. What do you think might be true?
The opposite?
Yeah.
Like,
And sorry, I don't mean to interrupt you. You're correct. And the mathematical term for the flavor of opposite we're talking about here is converse. So the converse is true. Theorem. If f of x is differentiable at x equals a, then f of x is continuous at x equals a. This is a true statement. And I want to give you some synonyms for the words differentiable and continuous. The synonym for continuous you're already familiar with. Continuous is the same thing as connected. right? If the graph is one connected piece, no breaks, no jumps, no holes. If it's one connected piece, that's what it means to say the function is continuous. The synonym for differentiable that I want you to get baked into your head is smooth. If a curve is differentiable, that means it's smooth, no sharp transitions, nothing pointy or jagged about it. So continuous means connected, differentiable means smooth, gentle transitions. If you zoom in, things stay smooth. They never get crunchy or jagged or pointy. And now it makes sense. If something is going to be smooth, it's got to be connected. But it's possible to be connected without being smooth. So note the converse to the above theorem, to the above theorem is false. Not all continuous functions are differentiable. And since this is an honors class, I want to show you guys what's called a pathological function. So our example there of a continuous function that isn't differentiable was the absolute value, right? It's continuous everywhere, and it fails to be differentiable at one point. Mathematicians in the late 1800s and early 1900s were very interested in coming up with examples of functions that take this sort of bad behavior to an extreme. I have here one of my favorite books. This never leaves the side of my desk. It's the only book besides the books I lecture out of and a few others that always live next to me. Counterexamples and Analysis. You see the coffee stains. I love this book. It's out all the time. It's a great, great book. One of the best things in here, and I'll show it to you on Wikipedia because it's easier there than it is elsewhere, is a function that is continuous everywhere in its domain, but is differentiable nowhere in its domain. I think it's, yeah, sometimes called the devil's staircase. This is it. Yeah, I always just called it the Weierstrass function. This is a function. Look how fucked up that graph is. No matter where you look at this thing, it's always connected. It is continuous everywhere. But it's not smooth anywhere. Even the pieces that look here like they might be made up of straight lines, if you zoom in on them, they are not. Oh, that didn't work. No matter where you look, if you zoom in, you find jagged peaks. At every single point, there is a jagged peak. They're trying to exemplify that by saying, here we've zoomed in on this little small part. And it's symmetric. It is an even function. So you might think that, okay, well, this little bit down here looks like it might be a straight line before I get to that peak, but it's not. If you zoom in, even the part that looks straight from far away is made up of infinitely many jagged little peaks. This function is continuous at every real number, but it's differentiable nowhere. So this is a pathological or maximally pathological counterexample to that tempted theorem. Here's how you construct it. You construct it as a limit of other functions. And showing that it's continuous everywhere is really difficult. Showing that it's differentiable nowhere is somewhat easier. If you want to actually construct this function yourself, that textbook Rudin that I referred you guys to last week has a construction in it, an explicit construction. And if you take a class like Advanced Calculus or Real Analysis, you will go through the construction. It's fairly complicated. but it's not impossible. It does exist. It is a very real function that is continuous everywhere. It's connected, but smooth nowhere. It's never differentiable. So that's a cool thing, right? One of my favorite true-false questions on exam 1 for Calc 1, if a function is continuous at x equals a, then it is automatically differentiable at x equals a. And the answer to that is, well, it's in the chat. I'm confident it's here. False. Good, good, good. Very good. Okay. Where do we go from here? I want to talk to you a little bit about logic. So the theorem above, it's another note. The theorem above is of the form A implies B. If you are smooth, then you must be continuous, right? And that right arrow, the bold right arrow there, you've seen me use symbols like that a few times in class. This is logical implication, meaning if the statement A is true, then the statement B must also be true. This is called an implication, and it's equivalent to, logically equivalent to, what's called its contrapositive. So kind of two new logic words for us today, converse and contrapositive. The contrapositive is if B is not true, then automatically A is not true. So if you are, this symbol stands for not, if you are not continuous, then you are automatically not smooth. This is true. So the word converse, the converse to a statement like A implies B, is the statement B implies A. A implies B is totally independent of the statement B implies A. However, A implies B is logically equivalent to the statement not B implies not A. One of my favorite examples here comes from a book by Miklos Bona, referencing the movie Office Space. If you give me some matches, then I will burn down the building. Suppose you come to work the next day and discover the building has not been burned down. Then you can deduce from that that nobody gave me matches. All right? I think it was actually right. If you don't give me my stapler, then I'll burn down the building. But I don't want to include other like not statements in here. So if you give me matches, then I will burn down the building is logically equivalent to the building hasn't been burned down, therefore nobody gave me matches. It's not the same as saying the building has been burned down, therefore somebody gave me matches. Someone else could have burned the building down. Thing could have been struck by lightning, faulty wiring, who knows? But getting comfy with logical statements like these is valuable if you want to go anywhere in mathematics, because it's all built on first order predicate logic, which is what this is. Okay, how are we doing on time? We have time for some more examples, or are we cooked here? 12:10. Let's see, this is an 11 to 12:15. We got 5 minutes. So let me talk a little bit about vertical tangent lines. One of your homework problems is to sketch the graph of f primed using the graph of f of x below, where the graph of f of x does some funny shit. Some shit like this. Now, if I pick a few points in here, there's something kind of interesting that happens. As I get closer and closer to 0, these tangent slopes, they get steeper and steeper, right? Again, out here, as I get closer and closer to 0, those tangent slopes get steeper and steeper. They get shallower as you move away, and they get steeper as you move in. So over here, maybe m tan is like -1/2. Here, maybe m tan is like -2. And then in here, it looks like m tan is getting really steep, like -100. And over here, same sort of thing, right? M tan is like +100. You know, maybe over here, m tan is like +1 or +2. Let's make it symmetric, we'll pretend. And over here, m tan is like +1/2. So if I wanted to try and draw the graph of f primed, we'll say this is like -2, this is like -1. F primed of -2, we said is like -1/2. F primed of -1, we said is like -2. F primed of, we'll call it, 0.1, we said that's like -100. F primed, -0.1. F primed of +0.1 is like +100. F primed of 1 is like 2, and F primed of 2 is like +1/2. If I wanted to graph this, I'll mark here 1, 2, -1, -2. I've got -2, -1/2. So I'll mark this as like -1. I'll mark this as like +1. -2, -1/2. -1, -2 are already way down here. And then -0.1 would be way, way, way down here. So we're flying off to -infinity in this direction. And over here on the other side, I've got something similar going on. F primed of 2 was like 1/2. F primed of 1 was 2. And F primed of 0.1 was like way up there at like 100. So we were doing something like this. I'll do my best to draw for you a picture here with the limited space I have. What you see is that we've found a vertical asymptote for f primed. So places where f of x has vertical tangent lines, like this function does near 0, right? These tangents are getting vertical. F primed has vertical asymptotes. And your homework will let you explore this. They have a handful of different examples, but I just wanted to kind of show you that because we had a few extra seconds at the end of class. So I'm going to leave it here for today. Remember, next week, you guys are going to be taught by Haley, Tahara, and Thomas the first few days of the week. I will, of course, be there to help wrap things up at the end and kind of hold things together, make sure everything is nice and cohesive. But please be respectful and kind to your student lecturers next week, because you are going to be a student lecturer down the road, and I'm sure you all want kindness and respect from your peers on those days. So please make sure you're on time. Make sure that you come and take good notes and participate in the same way you would for me or any other professor, because your peers have worked hard prepping these lectures and they deserve the same respect that anybody else does. Questions for me before we depart? Okay, then. I will turn you guys loose. Please try to finish up that homework by Monday. We will have lots of fresh stuff next Monday, when we will start talking about the derivative operation being done through some tricks rather than being done directly by the limit. We're going to prove a handful of rules for cooking up the formula for f primed so that you don't have to go through this limit process every time you want a derivative. I'm sure everybody will be happy with that, but please, while you're working through this week's homework, every time you need a derivative, do calculate it using the limit. Don't try to hack your way through with any rules or tricks you remember from high school. Do yourself the honest favor of practicing drawing the graphs and calculating the limits, calculating the derivatives using the limits. It's an important skill, and it is a skill that I will be testing you guys on. So this sort of thing will show up on exam 1, I promise you. So please don't cheat yourselves on it. This sort of thing will show up on exam 1. Don't cheat yourself on it. I know that this homework can be blown through quickly if you're kind of hacky about it. Don't do that. Show it the respect it deserves. Make sure you're really understanding the connections between the graphs of f and the graphs of f primed. Thomas, okay, I will make note of that. But yes, we absolutely should still meet on Monday. Just make sure that you send me the links, so upload your videos and send me the links by Monday so that we can review them together. And if there are any changes we need to make, we should. I recommend doing it in multiple short videos rather than a single long video, because that way if we need to make changes, you don't have to go back and redo everything. Any other questions before we head out? All right, you guys are awesome. Stay in contact with me over the weekend. If you need help with anything, just send me an email. I do have an office hour today, so if you want to come by that, we can talk there as well. Otherwise, I will see you all on Monday. Have a safe and happy weekend.